Hello, so in this video, I'm going to talk about material structure determination using X-ray scattering and diffraction technique. This video covers all the basic idea about how to determine the material structure using your X-ray data. And in the end of this video, I'm gonna do demonstration in a kind of step-by-step fashion, how you wanna do actually the material structure determination. It's pretty easy. All software you need is just Excel, Microsoft Excel. So you should be able to do it by yourself. Sorry. So now this is the roadmap of today's video. So I'm going to talk about how to determine material structure using X-ray scattering and diffraction. There are only three basic steps. First thing is you need to identify the parameter to be optimized. It could be d-spacing, it could be lattice constant, or it could be the crystal strain, or some people wanna know the crystal domain size, or like anything. First thing you need to know is what you wanna know. Second, you need to make initial assumption. Like this initial assumption is pretty important step, and it's gonna basically determine the fate of the fitting process. So this is pretty important. The third one is just minimization of the difference between experimental and calculated result, which is called the optimization process. So this can be done using the Microsoft Excel, as I said. And in the end, you will get the overall result. And important things is you need to make sure if it does make sense or not. If not, maybe the parameter cannot be determined or initial assumption is wrong. So if this doesn't make sense, you have to start over from step one, and basically you repeat this process until you got the nice satisfactory result. In the end, you can determine the structure of your material. And like I said, I'm gonna do demonstration in step-by-step fashion using just Microsoft Excel. So in this section, I'm going to explain what type of equation you wanna put in the Excel and how to use the solver. This is the function solver, which you can find in Microsoft Excel, so that you can do basically global fitting using the least square method. Okay, so from now I'm going to talk about actual process. Okay, so in this slide, my title is initial assumption is very important. So basically the idea of fitting is to converge some parameter. You're gonna always start with assumption, but assumption is assumption, so you have indifferent number of possibility, and from the indifferent possibility you wanna get the most reasonable value. So this is what you call fitting or optimization, right? And like I said, you're gonna conduct this slow process to make a nice optimization process. And in order to do that, there are only three things that you need. First one is, like I said, have a reasonable assumption. This reasonable, I deleted it, but this reasonable is very important term. And of course, you have to have your experimental result, and you have to have the calculation equation so that you can calculate the the theoretically predicted the value. And what I meant by reasonable is for example, when you have a nanomaterial with such as gold, it is reasonable to assume that for example, gold nanocrystal have similar crystal structure to the bulk gold material. So, but this is assumption. You never know. Your sample is your sample hasn't been measured by somebody. So it's possible that something miracle happens and you're gonna have different crystal structure, but it doesn't make too much sense by just changing the size. You usually don't get the different crystal structure. So your crystal structure of your nanomaterial is consistent with bulk material. So this is assumption, but this is reasonable assumption. So this assumption seems to be a good assumption. Even if you don't know, your, for example, material, crystal structure, it is reasonable to think that entropy plays a role to form some type of structure. So this type of assumption is pretty reasonable. Or another good way to have a nice assumption is you're gonna do another measurement, such as for example TEM can give you the good hint about the structure. So the structure that you can determine from TEM would be a nice starting point. So this is how you make initial assumption. And so basically my advice here is use common sense as a scientist. Okay, so I'm gonna use my experimental result. I'm gonna start with pretty simple one, which is FCC structure. So here I make a super lattice of nanocrystal, and when I take TEM result, it seems to be this pattern seems to be nice hexagonal based structure, which is consistent with 111 projection. I mean FCC structure from 111 projection. So first, from this TM result, you can make a reasonable assumption that this superstructure is FCC. And so let's use this assumption to determine the crystal structure. When I measure the small angle electron diffraction or small angle X-ray structure, X-ray scattering spectrum, this is the experimental result. So like I said, the first thing you need to do is you have to have a nice initial assumption. Second thing you need is experimental result, which is this. And now you see multiple nice peaks like here, 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 here. And by basically doing the fitting, you can determine the each peak position. Yeah, remember that this x-axis is Q. So in order to get the D spacing, you need to do 2 pi divided by Q. Then you can get the D spacing. So looks like there are multiple peaks, and now we need to check if these peaks are reasonable with the assumption that this superstructure is FCC. So the third things you need to know is how to calculate the D spacing. FCC is one of the most easy example. I listed several the equation to calculate the T spacing, and FCC is face-centered cubic. So this is the cubic system, and there is a selection rule. So this one. So in order to calculate the D spacing, the only parameter that you can change is this A. HKL is lattice index, and the first diffraction peak that you can see from FCC is 111. due to this selection rule, and the second one is 200. So this HKL is determined by the selection rule, but A can be changed. So you want to have the reasonable A number, and basically you want to compare between your like assumption that you are having the FCC structure in this super lattice and the experimental result. And the way you want to do the optimization is basically in the least square method. By using the least square method, you can optimize and you can minimize the difference between calculated value and experimental value. The idea of like the equation is this. You are going to add all the difference between, let's say this is experimental now result, and this is the calculation result. And you're gonna add up all the the difference between calculation value and experimental value. So this is calculation, and this is the experimental value. The reason why you wanna put the square here is because you wanna have the absolute value. So it doesn't matter if it goes higher, or lower. You just wanna know the difference. That is why you are going to put the square here. And you wanna sum all the difference between experimental value and this one, which means you summing up this one, this one, this one, this one, and by changing the y little by little, you're gonna get the most optimal y value to minimize the difference between the experimental value and calculation value. And in the end, you can have the optimal A structure like this. So basically this is the idea. So it's pretty simple. Just calculation is a little complicated, but if you go one by one, you should be able to do it by yourself. So that is why today I'm going to show my Excel sheet, how I calculate and how I do the optimization here. Okay, so this is the calculation, and here I want to use a little complicated structure. So here I use this triclinic structure, and in the triclinic, the equation to get the d-spacing for triclinic unit cell is very complicated. You're gonna use this type of equation, and for the lattice constant for unit the triclinic structure, usually A not equal B not equal C, and alpha not equal beta not equal gamma. So this is the lattice constant, and this is the angle of the unit cell. And you wanna plug these number in here to get this S11 value. This S11 value is going to here, and you are going to use HKL value. If you see the diffraction from, for example, 10. For example, if you see the 100 diffraction pattern, you're gonna plug 1 into H, and 0 into K, and L into 0. So this is how you do. In this Excel sheet, basically I put this equation. So this S11 is B square C square and sine alpha square. Just remember that the Excel use the radian for the angle. So I just convert this normal angle to radian, and basically you plugged this number into here, this number into here, this number into here. Same things has been done for S22. Excuse me. And S33. And for S12, again, I did the same things. A multiplied by B multiplied by C square multiplied by cosine alpha, cosine beta, subtract by cosine gamma. So that's how I create this value. Oops. And the way you calculate the d-spacing is, so basically first I calculated all of these values. So yeah, it is highly complicated, but the idea is pretty simple. So now we can calculate the 111 to 0. I mean this S11, this S value and the B value. And basically what you can do is you put all the equation of this equation here, and you gonna get this inverse d square value, so that you can calculate the d value. So this is the calculation result of your d-spacing. What you wanna do is you wanna compare between your experimental result, which is I listed all the experimental results here, and you wanna know the difference. So how I did was in this section. So this is different section, and if you look into this one, this is basically getting the square of the difference between calculation value and theoretical. This is the difference between the theoretical value and the experimental value. And for each peak, you can get the difference between the calculation value and the experimental value. Like you can see here, this is the second peak, and here this is the third peak. And so now I have a 1, 2, 3, 4, 6. So 9 peaks, and for each 9 peaks, I took the difference between the calculation and the observation. And so you want to minimize the sum of the differences. So which is this one? So basically I added up all the differences value of each peak. And you want to minimize this number by changing the, for example, A, B, C, alpha, beta, gamma value. The way you want to do is using this data and this solver function. You can do that. So in here, the purpose of this calculation is to minimize the sum of the difference. So we want to set the objective as here. So you see that now this is the objective, and we trying to minimize this. So you want to place this minimize, or you can put value of 0. It's same thing. So it's not gonna be the negative value since we got the absolute number. But so in this calculation, the minimize and value of 0 means basically same. Let's put minimize here, and changing variable is the unit cell in this case. So you can select these unit cell parameter. So this is basically how you select the objective and the changing variables. Now, if you are a constraint, you can add constraint, but let's give it a try, just using this value. The way you wanna do is just click solve, pretty easy. And you just wanna wait for a while, then you get the, optimized value. Now you might realize that these numbers are a little different from that. And if you compare the sum of the differences and this result, you'll see the difference, which means that these spacing, these lattice constant are optimized through the least square method. So that's how you determine the structure. I hope you understand, and maybe this would be helpful for your all of structure determination process. So please let me know in the comment if you have any questions. Thank you for watching this video.